Hello, everybody. Today, Professor Malkhaz Bakuradze from the Tbilisi State University and Prague-Hradec Mathematical Institute of Georgia will give a first pass of his lecture on symplectic cobordism and the transfer. Yeah. So, please.
Thank you. First of all, I am very happy to be in Prague again, and I thank my colleagues, Andy and Amiran Javakhishvili, to inviting me on this seminar. Today, I will speak about obtaining some interesting relation in symplectic cobordism using a stable transfer map and K-theory. So I will try to speak as elementary as possible, because this job is very technical, but let's see what we. So I will start with definitions, and I have two lectures today. I will start with definitions, and maybe at the end of this lecture give some statements about results, and statements and some results, but proofs and very details I will give you next lecture, okay, as agreed. So let us start from not symplectic, but very nice theory by French mathematician Tom. Unoriented cobordism theory, just this is denoted by the omega star, and it studies real manifolds. No, with no orientation, just two closed and dimensional manifolds are said to be equivalent or bordant if their disjoint union is a boundary of some n plus one dimensional manifold W. So border of W is disjoint union of M and N. Actually, this definition gives some ring, graded ring, as follows. So we can define sum in this ring in equivalent classes simply by this take equivalent class of the union, disjoint union. So just direct multiplication gives multiplication in this ring, and gradation is very natural, just dimension of the manifold. And what is very interesting and brilliant theorem is by René Thom, that this ring is isomorphic to homotopy groups of some spectra, which is called now Thom spectrum, MO. I will explain what is MO now. So spectra in general is generalization of space. We have space, topological spaces, and category of spaces, but space can be generalized to spectra. This is complicated definition, but this category is even nicer than category of spaces. So definition of spectrum is defined as follows. So ON, this is orthogonal group of N, of rank N, and we consider Grassmannian. BON is classifying space of ON. This is classifying space of rank N vector bundles. So that rank N vector bands over N space X are classified by maps from X to BON. So And over BON, there is a universal vector band. This is a canonical band of rank n. So what is BON? BON as its points is n-dimensional spaces, subspaces in R infinity. Okay, this band is tautological. So fiber is this n-dimensional points of this n-dimensional subspace itself. This tautological band, but this is universal band. So any band can be obtained from this band as pullback. So any given band over B, any B. So tone space, what is tone space? It's just take 1 point complexification of the total space. Okay. And for the universal band, we can define this M O N as tone space of this tautological band, gamma n. So now, repeating this, what is the tone spectrum? MO is just sequence of tone spaces, MONs, together with some maps, which are called structural maps. So this inclusion ON in ON plus 1 induces map between classified spaces. That's why between tone spaces, MON, 2 MON plus 1. And if now takes suspension of MON, these can be mapped in MON plus 1 as follows. So what is the pullback under the map MON to MON plus 1? The BON to BON 1 plus 1. Pullback is if we map BON to BON plus 1, induced by inclusion. So this band, gamma n plus 1, pullback here, gamma n plus 1 trivial summand, okay? And tone space of this, tone space of gamma n plus 1 is suspension of tone spaces, tone space of gamma n. And that's why tone space of this can be mapped here, which gives this suspension of tone space. There's maps called filter maps. So we have sequence of the MONs and the maps between them. And this gives spectrum where we have category of spectrum. And everything in this category is defined. Homology is and homotopies and everything. This spectrum is sophisticated, but even nicer than ordinary category of spaces. One example is the suspension operation has inverse there, in contrast to ordinary spaces. Now, in this job, in this theorem, the crucial role plays Pontrjagin Tom construction. And let me define this. What is this? Sometimes it's really called just Pontrjagin map, but anyway, what is this? We know that any manifold can be embedded in a sufficiently large dimensional Euclidean space, say Rn, n is large. Okay. And consider normal band of this embedding, nu M. Okay, M included in Rn, and now we can define this composition. What is Sn is just 1 point complexification of Rn, and we can take quotient. Yeah. We know that the neighborhood of this embedding, even M included in Rn, its neighborhood is homomorphic to normal band. Normal band. That's why we can quote everything outside this normal band, which will be top space of this normal band. So we have map from large dimensional n-dimensional sphere to top space of the normal band over M. This is called Pontrjagin map. So from manifold M, we obtain some element of homotopy group of top space. Okay. So this is main part, main tool in the proof of Thom's theorem. We need this definition of transfer map. So now what the whole structure? Okay, it's we have Thom theorem in terms of homotopy groups of Thom spectra, but algebraically, Thom theorem states that as a ring, omega star is a polynomial ring over some over Z2 field of two elements, and generators are all in all dimensions, but only 2k minus 1. These dimensions are excluded. So again, Z2 is field of two elements. This is xi are generators in dimension I, but this 2k to a power k minus 1, this dimensions 1, 3, 7, so on are excluded. Ring is polynomial. Its generators are realized, of course, by manifolds. So coefficients very easy, 0 or 1. And the seclusion is related to Adam's operation, reason of it. So that omega star is a polynomial rings in this generator. Now, we will need also stable transfer map. Stable transfer map. So again, consider vibration over B, and consider compacted smooth fiber. What is transfer? This works in direction of section. This is not section, but map in this direction, but not ordinary map, but stable map. This process means suspension spectrum. Suspension spectrum of B mapping to suspension spectrum of total space. The suspension spectrum is just sequence of suspensions of X, and of course, because of spectra, we have to have this structural maps are identity maps just because take suspension in any place The next one is exactly the same. So structural maps are identity maps. So that transfer is a stable map of Sturgeon spectrum. Definition, I omit definition is because it's very complicated, but it has very nice formal properties, and we will play on these formal properties. No benefit from the definition for calculation. I tried many times, but
Very nice.
yeah, I think I try. Now, okay, we have transfer, but how to calculate in these calculations? Very important role plays the so-called double coset formula. This is formulation for compact Lie groups. So for finite groups is easier, but we need this version. This version, I found this in original work of Mark Feshbach. So that what is formula gives us? If we take so we have G is G is compact Lie group, and H and I, H is closed subgroup, so that we have inclusion of groups H in R, and this is a fibration. Fiber is this quotient, but here we have BK. We are interested if computer to transfer in this direction, but in cohomology theories, it gives homomorphism. So transfer from H to G. This is homomorphism from H star PH to H star BG in this direction. And take any element, compute transfer homomorphism, and then pull back here. This formula gives the decomposition of this pullback element in several summands. Where here it's some K1, K2, and so on, subgroups of K. So pullback is sum of several summands. What is Euler characteristic of? So sum of this sum is our double coset space. We have H, H, G, H, K. It's a double coset space. This is not manifold, but union of manifolds. In many cases, we will have just segment, endpoints and interval, okay? Euler characteristic is not Euler, but you see that there is. Internal Euler characteristic. Consider this example for example. So that imagine that this double coset space is in segment. So we have three terms, endpoints and interval, okay? So Euler characteristic of internal Euler characteristic of xg. xg is component of the double space, double coset space. In this case, we have three summands only. Internal Euler characteristic means we have to take difference xj closer minus x closer minus x. So that internal Euler characteristic for interval is not 1 as usual, but -1. Because closure of the interval is segment. Is 1 minus closure minus interval minus 2. 1 minus 2 is -1. Okay. So this formula, we will need this formula improve for computing transfer in particular case. So we will compute this for spin bundles and projectivizations from spin bundles. So this formula will help us. This is the example, how to apply this formula. Simple example. So this G is unit quaternion or three-sphere, and K and H are just unit complex numbers or S1. Okay. What is double cosine space? Double cosine space, double cosine space, as I said, is the interval segment. So endpoints and the interval. And so that again, we have three summands in double cosine formula. So, but last one is 0 because, so double cosine spaces, S1 acting on S3, the quotient is S2. And left S1 acts on S2 by rotation. So north and second pole are invariant, and other points are yeah. So that isotropic groups for polars is S1, and isotropic group for other points is 0. So we have actually two summands because of this, and because of Euler's characteristic of the point is 1, we have exactly this transfer from S2, S1 for any element from BS1, any theory, including symplectic cobordism and others. So transfer from the unit is exactly 2A. So if we want to compute transfer from the unit, this will be exactly 2. This is surprising. Not in complex cobordism, but in symplectic cobordism, it should be Euler characteristic plus something. But in this case, exactly this one, 2A. This was example. Now, okay, this was for very nice unoriented cobordist theory. Now, let us turn to complex cobordism, which is also very nice. But now we have manifolds with some structure, not complex manifolds, but manifolds with stable tangent bundle as complex bundle. Okay, maybe so we have manifolds, real manifolds, tangent bundle, and add sufficiently large trivial bundle to get some complex structure in this.
There's some examples of not not complex. Does not have the complex structure, but the stable.
Yeah.
What is the symplectic example?
For example, any odd dimensional.
Okay.
How it can be complex.
Yeah.
For example, RP3, just one, and we get 4 times. Yeah. Okay. And here is defined what does it mean exactly. What complex number, you should know how the multiplication by this I, complex imaginary unit. Okay, and complex cobordism is also very good. Theory is very nice, computable. This is theorem. Polynomial ring in all even dimensions over Z. And what is even better here, that is coefficient ring, I mean mu star 4 point, this one. This biquillion is actually the same as universal Lazard ring. Universal Lazard ring. This is the ring of coefficients of universal formal group law. So what is formal group law? This is also a very nice theory and applied to define complex-oriented cohomology theories. Universal one is complex cobordism because of this Quillen theorem. So actually formal group law is not group but subseries in two variants with coefficients in some ring. Some commutative ring lambda, such that it satisfies some axioms like group axioms. So F X.
Some of the finite sum, infinite sum,
Yeah, yeah.
Okay.
Formal power series.
Yeah.
So like group axioms, X, Y is F, Y, X, and associativity. But okay, but why do you need? Actually, this is the apparatus for computing Euler class of two line complex bundles. If you compute tensor product over C of two line bonds, which is also line bond, should be some series in their Euler classes. Yes, actually, this is just. I think it was Novikov who observed this one, that coefficients of the formal group law generated all the complex cobordism. Novikov. And Quillen then proved that this is Lazard ring. Okay? So almost very close in time. Okay. So that's why the complex cobordism is very nice. Okay, we have, if you have formula for computing Euler class for tensor product, you have also splitting principle. So computation can be by this for any bonds reduce it to line bonds, and for line bonds you have formal group law and Cartan formula for Zudny sum. So you can machinery for computing characteristic classes. And if you have characteristic classes, you have characteristic numbers, and the element from this ring is determined by chair numbers, so everything nice. Now we move to quaternionic or symplectic cobordism, MSP, which is very difficult and is not computed, but up to some dimension. And no very nice computation, no. techniques, but people try many methods. One of methods I will speak about is getting relations, getting some relations using transfer and characteristic classes and K-theory. So again, this theory is difficult because no formal group law, and algebraically it's not polynomial, and it has torsion. In symplectic cobordism, no. The reason is that if you consider yes, but you know, is consider symplectic bundles, two symplectic bundles. Zeta 1, zeta 2. And K and tensor product, OH. This is not symplectic. Not even complex, but real. So Euler class, it has Euler class, but it's the orientation class, but not canonical class. So no canonical formal group law. And also the coefficients are in non-polynomial ring with the torsion, and so everything is broken here. So there is some works in this direction by Morava and Baker, I think, some twisting formal group law in for symplectic cobordism, but it's do not work as well as in complex cobordism in unoriented case. Okay. And also Buchstaber has two valid formal group laws. This is one, two valid formal group law. Okay, it's very serious theory, but formal group law in its usual sense does not work. Next. Now we start some facts in symplectic cobordism ring today and define some things we will need for the proofs next lecture. So we consider now some torsion elements, which is called now Nigel-Ray elements. Is PIs in dimension 8I minus 3. That is dimension 5, 13, okay?
Yes, you say some in the book. How it
Okay, now it's some writing, but consider the product of S1 on HP infinity or HP infinity BS1, okay? Or BSP1, HP BSP1. Quaternionic Grassmann. And consider tensor product. Eta is tensor product over R. Zeta is canonical. Line bond, quaternionic bond, or B. And eta 1 is one, real bundle. So this is symplectic bundle. It has Euler class, okay? But Euler class sits where its element in here. So it has form Euler class of zeta plus something. But this something sits in this suspension, okay? And its element has suspension of something. So it has a suspension of something, some series. Theta I, E, theta. Okay. That is why I think I write it so, and it's many people use this because of omit this first term. Okay. This one is relevant. Suspension of something, and there's coefficients, the theta is. Theta is. It turns out that they are torsion elements in symplectic cobordism. But theta 2I plus 1 are zeros. Yeah. That's why people relabel this theta 2i's by pi. These are zeros. And one exception is theta 1. One exception is theta 1. And that's use notation theta 1 and pi's. Okay. Theta 1 is
Yes.
this is result of Roche original paper. Yeah, this is publication. Only this is a theorem. And all the paper, the proof of this. We can see this in Roche, okay. On some torsion classes, it's symplectic cobordism, preplate even.
And so he didn't publish.
Yeah. Because Ray says that yeah. Don't like it.
So you put some paper somewhere.
I read this paper, very good paper. Why not publish? I don't know. I like this. Because maybe he moved to economics. He was student and quickly moved to other from mathematics to economics and never published.
So he proved reason when he was student.
Yeah, very young. Yeah, maybe PhD student. Okay. So that okay. Pardon. So we have there's classes for torsion part. And torsion part is only two torsion. So this ring, symplectic cobordism, has torsion, but only two torsion, not p torsion, only two torsion. So we have this one, theta 1, in dimension 1, and pi is p1 in dimension 5, p2, 16, 13, and so on. Relations about these elements. So Vershinin and he is co-author. Calculated this ring, symplectic ring, Cohomology ring, up to dimension 32, and then actually more dimensions. And he proved that most the ternary numbers of this element are not zero. But Gorbanov and Ray proved that some ternary numbers are zero, and phi, you know this formula, pi on this power is zero. So some interesting relations is known here. Now we define ray classes. Now I consider, in my paper, I consider this bundle over this product of quaternionic Grassmannians. And actually this bundle is symplectic bundle because it's isomorphic to realization and complexification. But we know that this is so symplectic Cobordism ring of what we know as P, HP infinity. We don't know what is coefficient ring, but if you know this, just over coefficient ring, this is polynomial ring, okay, formal series. So this is element sits in formal series in three variables with coefficients in now our unknown ring. Some coefficient of coefficients, we don't know the coefficients, but polynomial in x, y, z with this difficult coefficients. And consider these coefficients. Actually, observation is that if consider low dimensions, that dimension 4 or 5 or 6, this, they are present here, these eyes. And this is so up to dimension up to dimension 32 in Virginian's tables. This is of course takes place, but if you look, many of these I's and P's are playing major role here. Okay. So even they start from the beginning. Okay. Now what we want, the relations what I want to prove, next lecture as follows. So this one. So take any pi ray element by these coefficients are zero. And if multiply pi for these elements, then this pi replaced by pi is zero. Okay. So and similarly here, multiplication by phi lends this element to the CDL. And actually, who works in symplectic cobordism, it will see that this helps too much to compute differentials. But moreover, this is the main theory. You saw that more ternary products are not zero, but any fourfold product is zero. Any. And if consider double products, they map to the zero in self-conjugate. If we forget symplectic structure, we are in self-conjugate. So this double products go to zero here. So the second part will help in if conjugate, self-conjugate cobordism, which is not computed as well. Okay? Because double products are in lower dimension, and it may help. Okay. I have some. what we are going to do here. So again, I have the proof of the second theorem, but long time ago in transactions of IMS, but it contains mistakes, not my mistakes, but mistakes of quotation.
Yes, it is the sum.
Yeah. Because very famous, we will see, papers contains very simple, silly mistakes. But I was young and I believed, without checking, I accepted that. And that's why after some long time, I decided to review this proof and use only K theory and double coset formula. I discussed it this many times with Mark Feshbach. And we discussed this formula. I tried to understand everything. And he believes in this formula, okay? So that I believe this, that now everything is okay. So I try to use minimal things and check everything. Okay.
So is there some relation you mentioned about the gate theory? So
For example, yeah. So for example, what is so relations which we obtain here? Try to use simpler things in proofs, K theory or geometry, then transfer and some computations in some I don't know tables and apply some formula which never could be checked. Who will check? Okay. For example, there is a guy Kochman. He computed high dimensions, but how to check? It's impossible to read. Just okay, you cannot ask, cannot check, and okay, I appreciate, but I prefer to even it's monster. What you can obtain should be can be readable. Okay. Let me.
So then also okay.
Okay, I wanted to consider some, but it also takes time. But just to mention, you can think just to ask, and next lecture I will continue. So consider this vibration B again BAS1 or BAS3. This is complex projective space. This is quaternion project. Okay. And in many cohomology theories, this projection is fiber is S2, and P star is monomorphism in complex cobordism, in ordinary cohomology, in K theory, and so on. Now, question is, what about symplectic cobordism? Is this P star mono or not? Answer is no. If no, it's very interesting. What is the kernel? Because this kernel, some formal series in one variable, okay? And taking into account this is sphere band of the universal band here. Sphere band of the universal three-dimensional band here, spin band. This in other words, this is spin 3. PS3 is spin 3, and we have universal spin band, and this vibration is sphere band of spin. So this kernel will be Euler class of, and we will play on this. Okay, this is just task for up to the next lecture. Okay. Mhm. Thank you.
I would like to ask you something.
Yeah.
From your lectures, the theory of the oriented Cobordism and the complex cobordism is a very well understood.
Yeah, yeah.
And symplectic is a kind of mysterious.
Yes, of course, much more mysterious. Not only everything is understood in the theories, but coefficient ring and machinery is well advanced and promoted, and so
So the main thing is to understand formal law.
yeah. Formal law. I can speak something about this two-valent formal group laws. Its coefficient also sits in symplectic cobordism, and it has some properties. It also gives some relations. Works of Buchstaber and Bakuradze and others. Two-valent formal. This is a long paper by in Uspekhi, some periodic works in Russian, and it's translated also by Buchstaber. Theory of two-valent formal groups and applications in cobordism.
So if there are no more questions, then let us thank.
Thank you. Thank you.